All right, good morning. Music has died down, so that means it's my time to speak, which I'm going to be doing for the next hour. I hope you've been enjoying the conference. I've been here myself for quite a few years, and I truly, absolutely enjoy it. There's a lot of great content, a lot of great speakers. I'm not sure if I counted that. No, I'll do my best to make it great as well. And this morning we're going to talk about API security. All right, we're going to talk about various aspects of API security, 7 things. To be honest, I'm not going to keep counting my slides. Doing 7 things about API security is also very, very easy because there's a lot of stuff we can talk about, a lot of different ways we can talk about API security. And that's exactly what we're going to do. And if you ever need to talk about 7 things, well, having a list of 10, like the OWASP top 10 for API security vulnerabilities is a very good starting point because you can just tick them off like, yeah, 1, 2, 3, 4, 5, 6, 7, and off you go. This is a document released by OWASP, non-profit organization, aiming to improve the state of web security. And they had an OWASP top 10 for a very long time, like 2 decades or something. And a couple of years ago, they realized that the top 10 for web applications wasn't really directly applicable to APIs. Like some of the things mapped, of course, and other things were like UI specific, which is not relevant for APIs. And that's when a couple of people decided, like, yeah, let's create an API top 10. And that's how this project spun off. And today, it's actually kind of a very influential list. It gets updated every couple of years, a few minor changes, tweaks. Some issues rise, some issues drop, new issues come into the list, and so on and so on. This is not an exhaustive list. This is not a checklist. Like, this is not like, oh, we're going to do API security. Here's a list of 10 items, and if we're done with the list, then good job. We have finished our API security program, and we are now secure. Check. I know some certifications might work that way, or some vendors think that this works that way, but that's not the goal here. This is an awareness document. Like, it's basically the goal here is like, yeah, if you're doing APIs and security is not really at the top of your mind, maybe this is a good starting point. Maybe these issues that we see in like an enormous amount of different APIs, maybe you want to look for these things in your APIs as well. And that's kind of what this list is supposed to be. And that's also why I'm going to talk about quite a few of the items on this list right here. And we'll do that with me talking, explaining things, showing you cases, and I have some demos as well that are always a bit more entertaining than just me yapping and showing PowerPoint slides. All right, we're going to talk about concrete cases. We're going to talk about a smart scale that wasn't very smart. Well, not the scale, but the app behind it was, of course, a scale with an app, and the app had an API, and the API had virtually no security. And there's a lot of lessons to be learned from that specific story. I'll get back to that in a bit. Lesson number 1 basically would be, if you buy a scale, buy a dumb scale. That would be a very good life lesson. The operation of weighing yourself and entering that information manually in an app is probably not gonna be that problematic in your life. You don't have to optimize that final step because the consequences are not ideal. Second story we're going to discuss, that we're going to start with that one in a bit, is a case at Dropbox. It wasn't a breach, it was something that was discovered by an ethical hacker and reported, and Dropbox was like, oh crap, we kind of screwed it up. And that's going to be about server-side request forgery. And that's actually pretty interesting as well, because it's one of these nasty problems where it's very hard to apply the right defenses. All right, so that kind of sets the agenda. That's the warming up to keep you engaged. You can have like a counter if you want to about 7 things, and then you can harass me later whether I met the quotum, yes or no. All right, this early morning here in Oslo, I'm Philippe De Ryck. I'm from Belgium, and I'm a security expert. So I did a PhD in web security, which seems like ages ago, which probably also is ages ago. And right now, or since then, I've been helping developers understand security. So I understand a lot of very complex systems, systems using OAuth, OpenID Connect, API security, and so on. I help developers make sense of that, understand what's going on, the pros, the cons, the trade-offs, how to secure things, best practices, and what applies to you. And I do that in various ways through workshops. I did a conference workshop right here at NDC Security, so some of you were there. It's great to see you back here again. Means you're not tired of me yet, so that's good. I also do that with online courses and specialized consulting. So I join a company for a couple of hours per week and help them understand things, answer questions, work out potential scenarios so that they can move forward. All right. Finally, I also organize SecAppDev, and that's my volunteer work. It's a non-profit course in Belgium It runs every year, a week long, and we bring in experts from around the world to teach about application security. All right, it's all about secure application development. It's really awesome. It's the perfect opportunity to visit Belgium. If you're there for a week, you can try all of our delicious activities and tastings. That's definitely a pro. And of course, you get to learn about application security in this very intimate, immersive setting. Highly recommended. Small event, 80 people max, because we want to keep it that way so that we can learn from each other, enjoy each other, and have a great event. All right? So look it up if you want to. It runs in June this year. If you want to grab a copy of the slides, here's a very safe QR code. So that's test number 1. Will you scan it or not? No, it's fine. It just points to my website. You'll find the slides on my website. It's very easy to find. You can find them on my social media handles as well. And well, just Google my name. That's one of the benefits. If you get my name right, it's very easy to find. But step number 1 is getting it right. That's unfortunately something I can't change, so it's something you'll have to deal with. All right. Good. Let's talk about, oh, sorry, someone was taking a picture. Here you go. There's a timer like 10, 9. No, it's it's perfectly fine. All right, so first topic was, like I promised, server-side request forgery. And server-side request forgery is this very weird thing. And in general, either it applies to you, and it's very relevant and very, very dangerous, or you don't care about this at all. It's like there's usually no in between. It's like, oh crap, or whatever. So let's talk to the people that might have this problem. And let's start by defining what the problem really is and why it matters so much. And why it matters so much is because in our applications, we always have this line somewhere, right? We have a line that's the perimeter, the VPC, firewall, a WAF somewhere, shielding our environment from the dark, dangerous world, right? So that's essentially how systems are built. That should not be the only defense. There's talks about that here at the conference. You shouldn't rely on your WAF for everything, but it's not bad to have some perimeter in place somewhere to separate the nasty outside world from the pretty inside world. Well, pretty, depends on your point of view. But on the inside, we have our systems, we have our backends, APIs, servers, whatever is running there. And on the outside, of course, we have the attacker. And more than once, that brings me to the next slide, more than once people have argued, like, yeah, but this system is running internally, and we trust our people. Like, my colleagues are not the adversary. Usually not, but if something goes wrong, that already crumbles down. And there's an argument to be made, like internal systems don't have to be secured that well. Like, it's fine to be a bit more lax here and not do the strictest security. And this is a confession slide. I'm not going to ask you to confess here, but we've all done that. Right? We've all made that argument at some point, like, yeah, should be better, but for now it's fine because it's internal, and 5 years later it's still fine because it's internal and it never reaches the top of the priority list, and so on and so on. In general, you could argue like, yeah, this is fine. However, server-side request forgery is this type of vulnerability that has the nasty consequence that if the attacker can exploit it, they get a foothold inside your network. Server-side request forgery means that the attacker can control the destination of server-side requests, and sometimes even more than just a destination. And that means once the attacker can execute that vulnerability, they can start accessing things on localhost, right? That service on localhost where you said, like, yeah, nobody has access to localhost, so it's fine, we can just keep it like that. Or internal servers, internal APIs, all of a sudden become reachable with server-side request forgery. And that's the nature of the beast, that's the danger of SSRF. So how does that happen? Like, who comes up with that? Like, how on earth do we have an SSRF vulnerability in our applications? Well, whenever you accept URLs as input, that's the general rule. There's other types and variants, like if you accept IP addresses or domains, or you automatically resolve certain things you find in logs and so on. But in general, a good way to analyze your systems for this is like if you ever accept a URL as input. The attacker can give you a URL, and your server-side code has like a code path that says like, hey, here's the URL, let's fetch it and do something with the result. And at this point, you're probably thinking like, yeah, that's kind of weird, but this happens a lot in things like a webhook. Whenever you have a system, at some point you're building a SaaS, and the customer's like, yeah, I want to get a call on my system when something happens on your system, and a good way to do that is a webhook. So you tell the customer, like, yeah, just provide your path or your URL here as a webhook, and when something happens, we'll call that webhook. Bam. Server-side request forgery. Because I can give you, if I'm the attacker, malicious user, I can give you any URL as a webhook, and you're going to call it. And that's a potential problem. Very easy to introduce just by not thinking about SSRF, bam, and you have a potential vulnerability in your system. Other places, if you do link previews, you're building LinkedIn and somebody wants to post something, you paste the URL in your LinkedIn post. What does LinkedIn do? Like, oh yeah, I'm going to fetch that URL and get some metadata and show you like the preview of the image and the title and the short content and so on. That would also be a potential server-side request forgery vulnerability. And there's plenty of other cases where this can go wrong. Image loading, for example, as well. Like you allow a user to provide an URL to an image to do some branding, like I'll pull in your logo and show this on the page where the users are accessing that and so on. And that's the case that happened at Dropbox. That was an image loading issue right there. So these things are there. If they're there, they can lead to nasty consequences. Real-world SSRF attacks have led to root access to virtual machines, because the attacker can now call an endpoint where there's credentials or create a new user somewhere and so on and so on. Very, very problematic. They have led to the leakage of AWS credentials. Like you can call the credential metadata service and you're acting as the identity of the system you're sending the request from, and that system had too much access because AWS is a bitch to configure, sorry for the language, and so on. So yeah, that's a consequence that can happen as well. And of course with those credentials, the attacker can escalate to other resources, assets, S3 buckets, extract a whole bunch of files and create a whole bunch of problems. All right. Scared yet? Good. Let's fix it. Let's look at fixing this. Let's take a look at the image loading problem. Like, this shouldn't be that hard, right? This is valid input, right? If you want to allow branding with a URL to an image, I can send you an image to mycdn.example.com/image.png, and that should be valid input. And then something like this should be invalid input, like a request pointing to localhost, that should be invalid, right? That's not acceptable because makes zero sense in this use case, also not for a webhook, and for all the other cases, this makes zero sense. So the question becomes, how do we protect against that? Well, a security best practice is to allow or to only allow what you approve and block everything else, right? That's why a block list is not a best practice and an allow list is a lot better. However, in this case, the allow list would be the entire internet, which is kind of hard, except for these hosts where you really don't want the attacker to reach. And that already flips the script, as in, we can't really follow this best practice. We can't really decide like, yeah, this is fine, because we have no idea. The only thing we can do is say like, yeah, internal systems, internal networks, maybe not. That would be a way to do. So that's a bit of a problem. And then the challenge becomes like, how do you determine whether this is, what the difference is between both? And the URLs, well, there's URL parsers, so it's not that hard, right? You can parse the URL, you can take out a host, you can verify that host name where it points to. It probably requires DNS resolution and so on. And then you can be like, yeah, this is pointing to like public IPs, it's probably fine. And then you do like fingers crossed and you send a request and you hope that things work out. And that's how you solve server-side request forgery. In theory. That's how you solve server-side request forgery in theory. In practice, it turns out that URLs are absolutely nasty. Like, before I dove into this, I was unaware how insane that world is. And it turns out that URL parsers have slightly different interpretations of a malicious URL. Not a legitimate, not a URL like the one I showed you on the slide here, sorry. Not a URL on the slide here. These URLs are very easy to understand. Like, there's not going to be confusion. Nobody's going to think that the bottom URL all of a sudden points to somewhere else. But if you use malicious URLs, like maliciously constructed URLs with, for example, 2 @signs, which is not really supposed to happen, but the attacker can enter whatever they want. It depends on who you ask what they will see. For example, here, the URL parsers in languages like Node.js, Perl, Go, PHP, Ruby, whatever, they see a request going to google.com. They will resolve this with DNS, find the public IP address, and they're like, yeah, good enough for me, and they would allow that server-side request. However, if you then actually send the request using another library like libcurl, very common for sending requests. A lot of language libraries rely on curl and libcurl for sending requests. Libcurl would parse this and see like, oh yeah, evil.com, awesome, bam. Which of course translates to the attacker will give you a URL, you think it resolves to google.com, you approve it, and the actual request goes to evil.com, which can be localhost, an internal system, and so on and so on. And you have now fallen a victim to a server-side request forgery attack because of this URL parsing mess that we have in practice. All right. There's other cases. There's a link at the bottom to the research behind this. It's from a couple of years ago, but there's a whole bunch of other cases where things can go wrong, where you can confuse the parser about ports and stuff like that. So definitely, if you're interested in that, definitely take a look at how that goes wrong in practice. This problem, exactly this problem, occurred at Dropbox. The people at Dropbox are actually really good. I'm a user, so I hope they're really good, but I also know a few people there, and they have a very good security program. They do a lot of secure coding, and Dropbox has a lot of solid security. However, in this case, they got bitten by exactly this vulnerability. So they had code in there that actually checked the destination. They said like, yeah, we need to protect against this, and the code that they used relied on Python's understanding of URLs. And they checked this, and they said like, yeah, this host is fine, and off it goes. And then the actual request was sent with a library using libcurl, and libcurl saw the other thing, like I showed you on the previous slide, and that is why server-side request forgery was possible in the first place. All right? This hasn't resulted in a breach. Their internal infrastructure doesn't rely on HTTP either, so it probably wouldn't have been a problem, but they said like, you know what, even though this probably was fine, we're gonna approve the bounty anyway, and they paid the guy that reported it, and that's a win-win basically. Dropbox fixing security and you getting paid, and off you go. So how do we fix this? Well, you can't really, you can try to say like, yeah, but if we use the same URL parser both when checking and sending, then we see the same thing twice, and that's probably going to be fine, but that's a very, very risky path, because it also means if you ever change the library that sends requests or something changes under the hood, you might become vulnerable again. So that's something to take into account. The best fix is to avoid this ambiguity, because that's the problem here. We have ambiguity, meaning that we have a URL that can mean two different things, and we're trying to reason about this untrusted, malformed data, which causes us problems. So what we can do is basically take away the ambiguity. We take the untrusted URL, we transform it into something that is easy to understand, either the google.com or the evil.com, doesn't matter, one or the other, and that's the URL we'll reason about, that we'll verify and use to send requests. And that's what they did at Dropbox as well, and I'll show you the more generic version in a second. So at Dropbox, they realized they shouldn't have accepted a host name in the first place, because it's always going to be their host. They host the branding images on their CDN, so they said like, okay, let's hardcode the host and just get rid of this altogether. But they also construct a safe URI. And in essence, what you do is you take the input, you make it safe, like unambiguous, single meaning URL, and then you reason about whether you want to trust it, and you use it for the server-side request. All right, so what does that mean in a more generic term? In a more generic term, it means we get the input on line, let me check here, line 1, we get some input from the user, we transform it into a single representation by parsing it with a parser. Doesn't matter which part of the URL it understands as the host, it sees one host. And with that parsed URL, on line 5, we reconstruct a new URL. We fix the scheme, it's HTTPS, nothing else, so you can't tamper with file schemes or Gopher or data or whatever, no. It's HTTPS. We take the host from this one parsed understanding, that's going to be the host, and that's going to be the path. And of course, you can add query parameters and whatever not, that's completely up to you. And at that point, you have no more confusion. That URL with evil.com at google.com has now been parsed into either evil.com or google.com, one or the other, and that's your URL that you're going to use from now on. And now you make your assessment like, do we want to trust this? If it's google.com, sure. If it's evil.com, probably not. And then, of course, once you've trusted it and stored it, later you can send a server-side request. You verify this again, but that unambiguous representation never makes it anywhere else apart from this input. It's handled and it's basically covered for the rest of your code base. And that's essentially how you counter server-side request forgery the right way. At input, whenever you accept the URL's input, you should stop, parse it, reconstruct it, and then you move forward. All right? That's in essence the takeaway to protect against server-side request forgery. First of all, realize that there's no easy way to do this with allow lists, usually. Depends on the use case, but typically you need to work with block lists, like blocking local addresses and local ranges, and then allow everything else. And if you accept URLs as input, you have to parse them once, construct them in an unambiguous representation, and then reason about whether you want to trust that, yes or no. All right. One down. let's talk about something else. Let's talk about broken authentication. Broken authentication, OWASP API Security Top 10 number 2. We'll talk about one later. 2. That's why I have numbers there, to keep me keep me straight. Number 2. Also, for you to verify what I'm saying makes any sense. Otherwise, this would not be very, very useful. And for this story, I want to go back to the smart scale. And the smart scale had a bit of a problem. Well, it had a lot of problems, more problems than non-problems, but sure. And on the API, you had accounts, like so many applications have accounts, and the accounts, of course, people can forget their passwords, so you have to deal with that, and they had a password reset functionality, as almost every other application has as well. And the password reset, you know how this works, right? You enter an email address and it sends you a URL with a secret code, and the secret code allows you to reset the password, and the secret code was 6 digits. Which is, sure, why not, right? Why not? And somebody figured out to break that, which is not that earth-shocking. What I'm going to do here, I'm not going to explain you how this works. Well, I am going to explain you, not on slides, but I'm going to use a demo. I have a demo to show you how these seemingly silly problems can cause massive issues in applications, and also how to fix this and avoid these problems from happening. All right? And then, of course, after the demo, I have some takeaways that we can look at as well. All right, so in this demo, I'm going to use a tool called Burp Suite. Burp Suite is a tool that's also used by pen testers because it has a lot of nifty features to inspect applications and tamper with requests and so on and so on. And one of the features I'm going to use is the Burp proxy. And the proxy basically gives you an embedded browser. This is a modified Chromium, and it's modified in a sense that it will send all its traffic through Burp. So all the communication between the browser and the server will be visible to Burp. We can inspect it and do whatever we want with this. And we're going to go to my application, Restaurate. It's about restaurant reviews. I like great food, great restaurants, and I like application security, so I use this as a training example for restaurant reviews. It doesn't matter much, just where the name comes from might make sense for this specific demo. What do we have here? Well, we have a very simple application. We can log in with a username and a password, and of course we have a password reset feature as well. So let me show you that first. Password reset, you enter an email address and you click reset password, and it sends you a password reset link. Like, you know how this works. You've used this countless of times in the past as well. So what does this mean? This means if you go to our webmail, that we have received a password reset link, and this link allows us to reset the password. You can already see in the URL that instead of 6 digits, I made it a little bit easier to attack 4 digits. The concept is the same, it just takes like 5 minutes longer to attack 6 digits. You can see that this is probably not the most secure system that we're dealing with. What does this mean? This means that if I want to reset the password for your account, if I can guess your email address, that would be step number 1. And then step number 2, I can reset the password for the email address and then guess the authorization code. Like the reset code, if I can guess that one, which there's not that many combinations, so I can do that, then I can reset the password for your account. All right? The problem is, I don't know your email address. I don't even know your names for most of you, so that's problem number 1. But I can start guessing with email addresses. But the thing is, this is kind of invisible. You need to know an email address before you can actually make this work and so on. And that brings us to another attack first, and that's username enumeration. And username enumeration is an attack where you can guess which usernames or identify which usernames exist in the system. And this is often discarded as like, yeah, it's not that important. Like, yes, but you can also learn that from LinkedIn by looking at our company profile and so on. Yeah, sure, but this is still something you want to take a little bit more serious than it's usually taken in practice. So what does this mean? This means we can log in into the application, username, password. There's nothing here because it's a demo application. And we can log out again, and sure, that's very exciting. I'm fully aware of that. If you log in with a wrong password, it doesn't work. Login failed, okay, sure. If we log in with a wrong username, it also doesn't work. This is by design, by the way. This is how password-based authentication is supposed to work. However, behind the scenes, what's going on now? We can go to Burp. We can look at the history here. You can see all the requests that we've made. You can see that we opened the password reset thingy here and so on and so on. That's for later. But now you can see that we have tried to, here's a legitimate login. This is a login with my very secure password test1234, and that has, don't steal that password please, thank you. And that has succeeded because we get this authorization token. This is from my account, not your account, so this is not very exciting. Here is the attempt for logging in with a not very secure password, but maybe a bit better, it's at least long. But that didn't work. It says invalid email or password, and it says here, when we use the wrong username, it also says invalid email or password. Now, some applications give different error messages. They're like, oh, invalid password and invalid username. That's a good tell. If it says like, hey, invalid password, that means that the username exists, but the password is wrong. In this case, there's no way to differentiate between both, at least not visibly. However, if you look at what happened behind the scenes, in this case, there was no user. In this case, the user was correct because it's our user, but the password was wrong. And if you look at the response times here in the last column, you can see that the last request, wrong username, returned immediately. It's like, oh no, we don't know who that is. And the other one took almost a second to complete. It's like, oh no, we don't know who that is. Actually, the password is wrong. We do know who that is. And that's a problem here because it allows a timing attack, right? Correct username but wrong password takes a second. Wrong username takes 2 milliseconds. Like, that might be interesting because it would allow us to attack the system. Now, before we dive in, let me open up the code just to show you why we have that problem. And the problem here is because what's going on here, don't look at my very secure database. What's going on here is that this code snippet here from line 43 to 53 shows you what's going on. We try to find the user. If it doesn't exist, then we return an error message. And if it does exist, if we found a user, then we have to verify the password. And verifying passwords is kind of supposed to take a long time. We're using bcrypt here, a password verification or password hashing function. It's supposed to take a long time to prevent brute force attacks. And that long time is basically what's causing that 1 second versus 2 milliseconds response time. It's the application checking a password, which is the wrong password, using a slow password hashing function, as is a security best practice. So how do we attack that? And this is really cool, by the way. In Burp, we can take the request with the, let me check make sure I don't do it wrong here. We take a request with a valid username, sure. Let's send this to the intruder. And the intruder is a Burp tool with a very ominous name. It's basically a tool that will allow you to launch a brute force attack. All right, so what do we want to do here? We want to verify if email addresses exist. So what we can do is we can make this a payload, meaning that we can insert different values for this parameter. And it's a simple list, and we're going to load a list of email addresses. This list of email addresses, I have downloaded that one from the dark web. No, seriously, you can just download a list of 50 billion email addresses or something like that, and that gives you a very good starting point to see whether they exist or not. Or if I'm attacking your company, I'm going to go on LinkedIn, look up your company name, and then click on people, and there's like, whoop, here's a whole list. And if I have one email address, like John, whatever, @company.com, then I can guess what the other email addresses are going to be. Well, for John's, it's probably John 1, 2, 3 as well, but that's a different story. So here's a list of email addresses that may or may not exist. All right. So what do we want to do? Well, we want to inject them here. We're not going to URL encode because, of course, we don't need that for JSON data. And we're going to configure Burp here to send one request at a time. Otherwise, the timing attack may get a bit confusing. So one request at a time, and we can start the attack. So let's see if. Let me quickly check that I didn't screw it up. Yes, we're all good. Has happened before, so always check before I run the demo. All right, so we see here that the requests are going out. And you can see response received here, like 1 millisecond, very fast. And then here, this one takes 831 milliseconds. As in, it's also very unsurprising that email address is victim@virtualfoodie.com. Kind of gives it away, but sure. This basically tells you that the application has tried to verify a password in the background. So it basically means that we have found an existing account. We don't know the password, of course, but we have found an existing account, and that might allow us to launch a second step in the attack, basically resetting the password to that account and taking control. All right. First, let's fix this problem. There's a simple fix for this, maybe not the most performant fix, but a simple fix would be to always calculate a password hash. because that way the system always calculates something that takes a long time to do. And in this case, even when the user doesn't exist, we're gonna check a fake password, just like check anything, and it will take some time to calculate. It will be like half a second, 1 second, something like that, and that should solve it. So if we try this attack again, we can repeat here. Now all of them will take a long time. And we can no longer easily differentiate between which user exists and which user doesn't exist. All right. Of course, you should also block brute force attempts on the login form and stuff like that. That should be defenses built in as well. They're a little bit more complicated, but they can definitely get you there. But this way, the timing attack is at least gone, and there's no more username enumeration. All right, so that's good. We have solved that problem. On to the next. What are we going to do next? Well, we want to log in as victim.virtualfoodie.com here. But we don't know the password, so we have to reset the password. So what can we do? Oh, we forgot our password. We now know which user exists, victim@virtualfoodie.com, and we can reset the password. And it's going to send a password reset mail to that specific user. All right? That's how this works in practice. We can't access that user's mailbox, otherwise all of this is kind of a moot point. So we can't access, you guys are the victims here, we can't access, or I can't access your emails, so I don't have the reset code to do, but we can guess what that reset code is supposed to be. So let's see if we can do that. We can go back here. We reset our password. Did we do it before? No, we haven't. So we have to do it as a normal user first. My bad. So I forgot my password, reset password. I can check my webmail. There's a password code here. We can look at that, set a new password, Oslo. Also not a secure password, just in case you're wondering. And we have reset our password, so we can now go back to the application. There's a link here. We can log in as this one. That fails, obviously, but Oslo now works. Awesome. This is very, very uninteresting. I'm fully aware of that. Here's the call to reset the password, right? So this was an API call. It's a POST request. It contains a code, like the 4-digit code, and a new password. The 4-digit code is linked to this account in the backend, so now it resets the password for Philippe@restograde.com. So this is the request that we would like to tamper with. All right, so we send this again to the intruder. What are we going to do? Well, we don't know what the code is, so we're going to add a payload for the code. Password Oslo, that's easy to remember, so let's keep that one. That's perfectly fine. And now we don't want a list. Well, we could use a list, but it's easier to just tell burp to use numbers, because it's going to be like numbers, so that's very easy. Let's do it sequential. Let's start from step 1 to 999. You know how numbers work, right? What's going on? There we go. And it's a 4-digit code, so we set it to 4, and now it does like 0001 until 9999, and one of these is probably going to be the right one. All right, so good. You're all encoding. Let's not. What else? Well, we can now also, let me go back here. It says new password set for something. So if you find that string in one of the responses, we know we have been successful. So let's set up response checking here. A simple grep should do it. Let's clear the list and add a new item to look for. New password set. All right. Resource pool, we're going to do 10 at a time this time because that goes a bit faster. And we'll start the attack. All right, let it run for a while. Always very exciting. There we go. So here's a bunch of attempts. You can see like 0001 and so on and so on. And if we sort on this column, there's one that has succeeded. And if you look at the response, it says like new password set for Valerie, victim@virtualfoodie.com. So apparently the code was 6546. There we go. So what does this mean? This means that the password for Valerie is now Oslo. So we can go here. We can go like I'm victim@virtualfoodie.com. The password is Oslo, and we log in, and we are now logged in as Valerie. Go from Restograde to the smart scale. That's the vulnerability at the smart scale. Whoops. 6 digits. So you can imagine to modify the attack, you set like number of digits to 6. You click start, and you wait like a few minutes longer, and you're done. That's in reality how these attacks work in practice. Now, this is a very, very stupid problem to have. No offense to the smart scale developers, but it's a stupid problem to have. First of all, brute forcing on password reset tokens is probably not something you want to allow. And you can be like, yeah, come on, who does that? Well, it happens all over the place. Facebook had this a couple of years ago as a case. They had a beta version of a new version of, I think, some Instagram app, and the beta version did not enforce rate limiting on the password reset endpoint, but it used live production accounts. So you could reset somebody's account through that beta app and take control of that. Whoops. So this happens in quite a few places. So brute forcing there, probably not something you want to allow. 4 or 6 digit codes, not great either. If you want to use like random codes, use long strings, like unpredictable strings, that's already a bit better. It's still not great though, because you still allow somebody to tamper with that. Why? It's a URL parameter. It's a parameter in the URL or in the post request in the body, and an attacker can easily exchange that value for something else. And that's something we can actually take away. What if we can include a value that's not just a string or a digit string or whatever, but we add maybe a signed object in there? Like an object that represents a token, and that token is for resetting the email for this specific user. If it's signed, means that there's data integrity as well. Means that if the attacker would like to tamper with that, the signature verification mechanism is going to fail, and we reject that upfront without even thinking about that. And that's what I want to show you next. We're going to update our application, so we're going to comment this line. We use these functions from the codes insecure file, and we're going to use the codes secure file. So let me show you what that means. Here, the codes insecure generated basically a random number using math.random, which is also really, really not good, because these are predictable numbers. Once you figure out a seed, the whole sequence is predictable. So that's also already a very bad start. So this is just crap. Don't use that. This one is a lot better, because here we're issuing a JSON Web Token. And inside the JSON Web Token, it's going to be a signed token. Inside the token, we put the email address of the user and a unique ID, and that's the data we will use to reset a password. And now, there is no way the attacker can tamper with that. I'm going to show you that. So we use this, we saved it, good. So let's go back to our application here. Forgot your password, reset password, and let's go to the webmail again. You can see that the URL is now a lot longer, and that there's a code in there. And whenever you see a string starting with EYJ, right, the first characters of the blue of the code parameter, EYJ is base64 encoding for open bracket. It means if you throw this in a base64 decoder, it's probably going to be a JSON object notation, whatever. And then a JOT has 2 of these strings, a header and a payload, and we can actually copy this value and drop it in a debugger. And somebody in my workshop told me that I should not use jot.io, but jot.ms. So let's do that. And we paste it in here, and you can see it decodes this. So the red part is a header, the blue part is a payload, the actual data, and the green part is a signature. And what it shows us here is that inside that token, we have, let me make this a bit bigger, inside that token we have an email address for the account we're trying to reset. We have an issued at timestamp, which is now, and we have an expiration timestamp, which is in 1 hour. All right? And what we're basically doing here is we're putting the email, we're no longer relying on random tokens, we're putting the actual email address in the token. So if the attacker wants to, well, we can use this as a user, so we can actually reset this. Haha. Don't worry, I reset the demo afterwards, so I don't have to remember the last crappy password I used. But if we look at this, and we go back to the burp proxy, we can now see that the reset password call includes this JSON Web Token. And inside the JSON Web Token is the email address. So if we want to reset the password for victim@virtualfoodie.com, we would have to change the value inside the JOT token, but that would make the signature invalid, and if the signature becomes invalid, the backend doesn't accept it. So what we've done with adding integrity to these parameters is preventing the opportunity. The attacker doesn't even have the way to tamper with this anymore, because that is entirely taken away. The only thing the attacker can do is take like another complete valid JOT and paste it in place, but they should not be able to obtain that. You can't guess that, you can't brute force that, so that's basically impossible unless you have access to the email address of the user. All right? So that is how you can fix this in practice, and that's the best practice. Good. back to our slides. Some takeaways. Do not buy a smart scale, seriously. It's not in the slides, but it's a very important takeaway. AppSec-specific takeaways, avoid leaking information, right? APIs very often leak information that shouldn't be there. It's timing attacks are one thing, like error messages are another. Make sure you don't leak that information. That's something you can take into account, you can actually look at, and you can approach. And there's a lot more advanced timing attacks as well, so this is definitely something you want to take into account for very sensitive operations that might result in the attacker learning binary information, like Boolean information. Does it exist, yes or no? That is a very, very useful feature, and you only need one data point for that, the response time. Implement rate limiting. Very, very important. There's actually like an OWASP API Security 10 item about not having rate limiting on your resources. This is absolutely critical on a variety of endpoints, especially on endpoints like password reset and authentication. You definitely want to take that into account, all right? However, be aware, rate limiting is kind of a cat and mouse game. As in, you can build like a super smart rate limiting policy, but an attacker using like 15,000 different hosts all over the world might still be able to bypass that one way or another. So rate limiting is good as a line of defense, as a layer, but it's not the only defense that you should have in place. And then finally, mitigate guessing attacks. Think about integrity protection of your data. This one is really important. I'll post with that for you if you want to. This one is really important because all too often we just drop parameters in URLs or left and right, and we allow an attacker to tamper with that. We actually do threat modeling and think like, yeah, the attacker can tamper with this data, so how can we ensure that this does not result in bad? Well, take away the tampering. That solves the problem altogether. Like, sign this using anything you want, but JSON Web Tokens are a very easy way to represent claims like this. There's a gazillion libraries for that, and there's a few best practices to take into account. That's stuff for a different time, but it definitely makes things a lot easier. All right, good. Number 4, by the way, unrestricted resource consumption. That is translates to not having rate limiting in place. I haven't highlighted it, but I've covered it. Just in case somebody's keeping count of how many things I have talked about. Let's talk about authorization. Authorization is kind of important. OWASP API Security 10 number 1 and number 5. So authorization goes wrong in a variety of ways. And unsurprisingly, authorization went wrong for the scale application. So what happened here? Well, somebody looking at this figured out that they could add family members to other people's families, which is like not great. And of course, that was a stepping stone for something else. So authorization is, I'm making fun of the scale here. If I ever run into those developers, I'm going to get a beating, probably behind the talk. So yeah, whatever, I'll take that risk. But the scale is one thing, but it's number 1 in the API Security Top 10. So it's not just a scale application, it goes wrong everywhere. This is a massive problem. So why is it so hard to get authorization right? It doesn't seem that hard, right? How hard can it be to not add family members to somebody else's family? Well, let's look at some examples. Here's a snippet of code of adding a member to a family. This is this is PowerPoint code, but whatever. And we check if the user has a role family owner, right? Checking a role before allowing that is a good way to enforce things like function level access control. That might be something you want to implement. However, code rarely looks this simple. It's rarely like, oh yeah, has role, who forgot about that? No, in reality, it's going to be a little bit more complex because you'll have different roles with different permissions. You'll have a role family owner, a role parent, a role admin, and God knows what else you can think of role-wise. And that means you suffer from a problem that's known as role explosion. Like a lot of different roles with similar but different configurations. And this policy is very hard to maintain. Also, having roles hard-coded in code, that's what you see. Whenever somebody talks about RBAC, you see this annotation-based or whatever, and this also means if you add a new role, you get to have the fun morning of going through all your endpoints and deciding if you have to type or has role my new role, and then you have to deploy the application. It's not really a good way to handle authorization. So while RBAC, role-based access control, may have its uses, be careful with that. That's what I'm trying to say. RBAC is probably a little bit too rigid for what you're trying to build in practice. How can we fix that? Well, we can add some abstraction in between. We have the role, we have the endpoint, and what we need in the middle is permissions. And by using permissions, we couple a permission to an endpoint or a set of endpoints, and then we can couple the permission to a user or to a roles of a user, and now we don't have to update our code every 2 seconds that we have to find a new role to add. And this makes things a lot better, a lot easier to understand, a lot easier to audit as well. Looking at endpoints like this, you can easily map the endpoint to a permission and say like, that seems to make sense. Versus with roles, you have to know about all of the roles and then decide if this makes sense, yes or no. So that's a very good way to solve authorization. All right? Seems simple on PowerPoint, goes wrong, or applications get this wrong quite often. So that wasn't that hard, right? I mean, come on. We can fix authorization in like an hour on Monday morning, something like that. However, we only covered so far number 5, broken function level access control. Number 1 is a bit more critical, and number 1 is broken object level access control. And that's something that is often overlooked or often goes wrong in significant ways. So what we've done now is we check if the user has permission to add a family member, because they're maybe the family owner, right? So if I have a family, I am the family owner, and I can add members to my family. Good. That's how I do this, with post request, create family member, and so on and so on. Awesome. Now if I want to add a member to your family, I'm going to use burp. For a very sophisticated attack, I'm going to swap out my family ID 1 for your family ID 7. And I got to send a request. Burp has a tool for that, repeater. You can modify the request, click send, and the application is going to check this like, hold on, authorization, do you have a permission add family member? Like, oh yeah, of course, Philippe is a family owner, of course he has. Bam, and we add a family member to your family, and now you have an extra family member, which is usually a happy occasion. In this case, very much not. So this is not something that's supposed to happen, and that is called broken object level access control. We never checked the object level access, the family level access, like is this user allowed to access this particular family? And this goes wrong in a lot of cases. For example, a SaaS with multiple tenants, like multi-tenancy, you typically have a header with like a tenant ID or a customer name, or it's somewhere in the URL or something like that. Forgetting to enforce that, like limit the user to their own tenant, can result in similar problems. Like create admin user, if I can do it for my tenant and I can do it for your tenant, 2 different cases that one is good, one is very, very bad. All right, so let's fix this. Come on, we're developers, we can solve this problem, right? And that's where things get tricky. Because to solve this problem, you have to implement fine-grained authorization checks. You'll end up with code like this, which is not great, by the way, but we have a permission check, just like before, and then we have to do an object-level permission check. And you can see this on line 4, and you can see this is super ugly code. And it's like basically if the user is a family owner or a parent, then we have to apply an additional check, and they have to be a member of this family. Otherwise, we should not allow that. All right, so that's, I'm not saying this is recommended code. The giveaway is that smiley faces are not a good way for handling exceptions, just in case you're wondering. But this is not good code in any aspect. Like, auditing code like this is a mess, right? If I come in and you're asking me to help you to assess whether your application is secure, and we have to review this, whenever you encounter rules like this, it's going to be a nightmare. And we're typically in a room with a couple of developers, and I'm asking, like, how do you check this? How do you enforce that this document can only be read by someone with permissions? And all of a sudden, everybody looks at one guy, because there's usually one guy writing authorization logic. And you see the guy thinking, like, yeah. And sometimes it works out. Sometimes they're like, oh, yeah, we actually should be stricter here. And sometimes it actually happens that they start writing code on the fly in the meeting where we're discussing security of the system, like, oh yeah, let me just fix it in code real quick. And they start writing additional rules. It's like, no. You can't do this. Well, you can, but it's not going to work out. The reason this doesn't work out is, first of all, it's going to be a mess. Every endpoint will have like a gazillion of these checks. It's not going to be pretty. Second thing is, the moment you add a new role or a new whatever, you'll have to go over the code again and be like, try to understand what you wrote like 2 years ago and whether it makes sense, and try to figure out if you should add something there, yes or no. And most importantly, a policy like this is impossible to audit. And if you have a policy like authorization that's about security, auditability goes hand in hand with security. Because if you can't audit it, if you can't assess whether your policy is secure, then you don't know if it's secure. So auditability is absolutely crucial. and you can ask the people in my workshop, I keep hammering on about that. Auditability is absolutely crucial. All right? So how can we fix this? Well, that's the fun thing about doing talks like this. I can tell you how to fix things. Well, you should pull out the authorization logic from your code. This is not maintainable. This is not auditable. This is crap. No offense. When you bring me into your company, I'll use more diplomatic language. Yeah, this can probably be improved, would be something. So what you want to do here is you want to pull this out. What you want to do is you want to use a policy engine. A policy engine is going to solve all your problems, especially if you talk to vendors offering you policy engines, they will promise the world to you. And then when you start using it, it's like, meh. But in this case, you don't need to buy stuff. You can just write your own policy engine. Meaning, in my case, in the smart scale case, you write one class with a couple of static methods where you check permissions. And what you do there is you basically pull out all of the nasty logic and you ask family data.add, policy.check permission line 3 here. We check permission, add family member, we provide the family, we provide the user, and that policy is going to give us yes or no, true or false. And the policy will go through the checks, like is the user an admin? Sure, allowed. Is the user the owner of this family? Then yeah, that's allowed. Is the user a member of this family with the right permissions? Then yeah, that's allowed, otherwise no. And that's essentially how you can solve this. And this is a very, very simple way, very cheap way of externalizing your authorization logic in a single file, which gives you a large amount of benefits. What it gives you is auditability. You can audit your endpoint code. You can even have like linting rules or code scanning rules that say every endpoint here has to call the policy. Check. You can never forget to implement authorization. Good. Second, you can audit your actual authorization policy and see whether it makes sense. You can unit test your authorization policy. You have methods here. You can write unit tests to see that the authorization policy actually enforces what you think it does, which again improves auditability. And since all the authorization logic is now centralized in a single file or a set of files, you can also prevent unauthorized updates. You can prevent somebody in a PR from changing some of the authorization logic, because that happens quite often, like something doesn't work and somebody starts messing around and maybe the AI tool in the IDE says like, yeah, maybe change this to that, and somebody does and oh, look, it works, and they commit and off you go. But they may have changed the authorization logic. I've seen this happen in practice, like a PR removing the check limiting a user to a specific tenant. It wasn't suggested by AI, it was just a mistake, but it removed that and it created a broken object level authorization problem. So having this centralized gives you a lot more control and allows you to basically address these issues. Now, centralization has a second benefit. You can do it in code. That's the cheap version, the simple version, which is enough for a lot of applications. But sometimes you're building something super complex, like a very complicated authorization policy, something that you can't easily check in code because it's just a behemoth of authorization. And that's where you want to involve like an additional service. Right? You typically have, some companies have this internally, like in banks, you often find like an existing authorization policy engine that you want to call and ask whether something is allowed. That's one use case, but you can also deploy something yourself with a tool like Open Policy Agent. An Open Policy Agent allows you to express an authorization policy and then deploy that policy alongside your API as an agent-based service where you can ask authorization decisions. You provided all the content and it says like, yes or no, or maybe conditionally, and so on and so on. And you can plug in other things here as well. Maybe you have an internal authorization service and you plug it in instead of Open Policy Agent. Or if you want to use OpenFGA, you want to plug that one in instead of a policy agent, and it can definitely help you make authorization decisions as well. But that externalization process here applies as well. Now it's not in code, but it's a separate service that you want to move towards. All right, so you want to centralize complex authorization logic. That's the takeaway here. It should not be scattered throughout the code, but it should be centralized in a location where you can control it, review it, test it, and prevent unauthorized updates. You want to empower auditability as well. I said I was going to say that this is important. I'm going to repeat it. Auditability goes hand in hand with security. If you can't audit this, you cannot guarantee that it's secure. Keep that in mind. Review your own applications for auditability. If you don't understand the code from a couple of months or years ago, then guess what? Nobody else will either, and there might be potential vulnerabilities there. Good. That brings us to the last item on the list, broken object property level authorization. Another authorization problem, but now we added a letter to the abbreviation, so it's not BOLA, but it's BOPLA. So in case you want to play abbreviation bingo back at your company, you now have a new one to put on the list, BOPLA, broken object property level authorization. Guess who had a problem with BOPLA? Seriously, this is going to end badly for me someday. But what's BOPLA? Well, there's two versions of BOPLA. There's a write version and a read version. The write version is mass assignment. I'm not going to talk about that today. That's maybe for some other time. But the read version is excessive data exposure. And it's basically a problem where the application or the API is giving the front-end data, too much data, but the front-end only uses a part of it. For example, here we have the API Security Swag Shop, and in the API Security Swag Shop, we show a list of online users. It's like a friendly community, and we show our friends that are online, and what we basically have here is we have 3 online users, John, Jacob, and Philippe, and they have IDs and names and so on, and the front end uses the name and nothing else. Except the API returns user objects, and users also have addresses because of shipping and so on, and we're returning that, but the front end just ignores that. So if you do like quality assurance of the front end, it's like, yeah, users, all looks good, awesome. But if somebody, an attacker, uses the application and the attacker has some mad skills, like they open up the dev tools in the browser, they go to the network tab. This is really advanced, like the network tab. You can see API requests and responses, and you click on the API request, and you look at the response data, and there's like a bunch of JSON, that JSON. So this means just by going there, you can obtain addresses of users, and that's excessive data exposure, and that happens quite a bit as well. Has happened with the smart scale by leaking access tokens and refresh tokens, something that shouldn't have happened in the first place, but happens in all kinds of places, results in a lot of real-world problems. Why do we have that problem? Well, usually because at some point we drop a domain object, like a user, a model, straight into a response, which gets translated to JSON, and that user object will have a couple of properties right here, which all get exposed. That's the whole problem. Whether it's an actual model or it's something in between, if you have too much data fields in there, they will get exposed, and you will suffer from this problem. How do we fix this? Well, there's annotations allowing you to hide fields. This is not a good practice. This doesn't scale very well. I don't know why I'm even showing it, probably because to tell you, don't do this. Adding JSON ignore annotations is not a good security model. It's not going to end well if you start doing that. The proper solution is to use DTOs or schemas or something that validates or restricts the data in the response. And in this case, it's a DTO, that's the Java way, because in Java you have to write a lot of code to get things done. But it works, and what we do here is we map our user objects. We still have users here, but we map them to something called public user info. And I'm always a very big fan of using expressive names, which matches perfectly with the Java ideology of making things very verbose. So public user info will help you as a developer, because if you're writing this or reviewing this or modifying this public user info, then you probably are not going to add fields like address there or password or something like that, because it will make you think like, probably not the right place to put these values. And that way we avoid sensitive data exposure or excessive data exposure, and we can solve that BOPLA vulnerability in our API. All right, that brings me to the last takeaway like this. I have some other takeaways coming, but you want to avoid directly exposing internal objects to the outside world, because it's very easy to make a single mistake, maybe not when you write the API endpoint, but later on, a refactoring like, oh yeah, let's add a field here, and all of a sudden that field will be returned here in the API endpoint, causing a potential issue. So you want to be careful with that. DTOs or in-between schemas or something like that is definitely the way to go to prevent this mistake from happening. All right, that brings me back to the overview of the OWASP API Security Top 10. In this hour here, we covered quite a few of these items. Of course, there's more, so keep track of my work, and you'll learn more about API security as well. I have some key takeaways. Takeaway number 1, the best authorization policy is, well, secure, but also understandable and auditable. If you can't audit it, you cannot guarantee the security. Like, really, really important. You want to analyze your APIs for data leakage, data exposure, and brute force attack vectors. That's something you definitely want to look for. to improve the security. And finally, perimeter security cannot be your only defense. It's still a good defense. It still should be there, but you should assume that at some point your perimeter will be compromised and internal systems will become exposed systems, and you need to ensure the security of these systems as well. If you don't, things are gonna end badly. All right? I'm running that 2-day API security workshop in Oslo again in May at NDC Oslo, like the big conference. So if you want to come there to learn more about API security, definitely take a look at that. And with that, I want to thank you for being here. I hope you enjoyed the rest of the day. And I'm doing a second talk right after this one. So if you want to learn more about OAuth in front ends, that would be the place to be. All right, thank you very much and enjoy the conference.